Hello everyone, my name is Prashant from BSc Chemistry on the second sem, and today we are going to read the chapter Electrochemistry. So here, electrochemistry is a branch of physical chemistry which deals with the interdependence of chemical changes and electrical energies. Such interactions are observed at boundaries between electrolytes and chemical electrodes dipping in item. Electrochemistry is the study of production of electricity from energy released during the spontaneous chemical reactions and the use of electrical energy to bring about non-spontaneous chemical reactions. Electrochemistry acts as bridge between thermodynamics and rest of the chemistry because it provides technique for both measuring the thermodynamical state functions and for predicting equilibrium concentrations of dissolving and reacting ions. A large number of metals, sodium hydroxide, chlorine, fluorine, and many other chemicals are produced by electrochemical methods. Battery and fuel cells convert chemical energy into electrical energy and are used on large scale in various instruments and devices. The reactions carried out electrochemically can be energy efficient and less polluting. The transmission of sensory signals through cells to brain and vice versa, and communication between the cells are known to have electrochemical origin. Terms used in electrochemistry: electrolytic conductance. The flow of electricity through solutions of electrolytes is used to the migration of ions. Potential difference is applied between two electrodes. The cations, which are positively charged, move towards the negatively charged electrode, while the anions, which are negatively charged, move towards positively charged electrode. Conductance G. The ease with which the electricity flows through a solution is called conductance of a solution. It is defined as the reciprocal of the resistance of the solution. G is equal to 1 by R. Unit of conductance is reciprocal of ohm or ohm inverse or mho or Siemens. Ohm's law: I is equal to E by R, where I is electrical current, E is potential difference, and R is resistance. Specific resistance: the resistance of any conductor R is directly proportional to L by A, where rho is constant, called specific resistance. If L is equal to 1 meter and A is equal to 1 meter square, then rho is equal to R. The specific resistance is defined as the resistance of specimen 1 meter in length and 1 meter square cross section. In other words, it is the resistance of 1 meter cube of the material. Unit: R is equal to rho L by A. Rho is equal to ohm meter. Specific conductance: the reciprocal of specific resistance is called specific conductance. K is equal to 1 by rho. It may be defined as the conductance of 1 meter cube of a material. K is equal to L by A into 1 by R. K is equal to S meter inverse. Equivalent conductance: specific conductance is suitable for only metallic conductance. For measuring conductance of electrolytes in solution, equivalent conductance is used. It is defined as the conducting power of all the ions produced by 1 gram equivalent of an electrolyte in a given solution. Molar conductance: molar conductance is defined as the conducting power of all ions produced by 1 mole of electrolyte in a given solution. Let us consider a solution containing C moles of an electrolyte in 1 cubic meter of solution. The volume of the solution containing 1 mole of the electrolyte would be 1 by C cubic meter. Rho m is delta m is equal to conductance of 1 meter cube of the solution into volume of the solution in meter cube containing 1 mole of electrolyte. Delta m is equal to specific conductance into 1 by C. Delta m is equal to K into 1 by C. Electrical transport conduction in metals and in electrolytic solution. Metallic conduction: the electrons can flow through metals, this properly being known as metallic or electronic conduction. The metallic conductivity is due to the mobile electron clouds permitting relatively fixed lattice of positive metal ions. When electrons are external battery are forced into the one end of metal wire, they displace the electrons of the cloud at the point of energy. The displaced ions in turn assume new positions by pushing neighboring electrons ahead, and this effect is transmitted right down the other end of wire where they are forced out and sent back to the external battery. The rate of which electrons enter from one end of the wire is equal to that of the emission from other end. At any point in the wire, the electrical neutrality is maintained. The quantity of electric charge is measured in coulomb. 1 coulomb is the charge carried by 6.2418 into 10 raised to power 18 electrons. The rate of flow of electric charge, i.e. current, is given in ampere. 1 ampere is 1 coulomb per second. The current is forced through the circuit by an electrical potential difference which is measured in volts. It takes 1 joule of work to move 1 coulomb from a lower to a higher potential when the potential difference is 1 volt. Thus, 1 volt is equal to 1 joule per coulomb, or 1 joule is equal to 1 volt coulomb, i.e. 1 volt coulomb is a unit of energy and equal to 1 joule. Electrolytic conductance. Electrolytic conduction, in which charge is carried by ions, will not occur unless the ions of electrolyte are free to move. Hence, electrolytic conductance is exhibited by molten salts and by aqueous solutions of electrolytes. The principle of electrolytic conduction can be illustrated by reference to an electrolytic cell for the electrolysis of molten NaCl between inert electrodes. Relationship between equivalent and specific conductance. To find out the relationship between specific conductance and equivalent conductance, imagine 1 meter cube of a solution of an electrolyte placed between two large electrodes 1 meter apart. The cross-sectional area of solution will be 1 meter square. The conductance of solution will be its specific conductance because we are having 1 meter cube of solution. Further, suppose that 1 meter cube of solution contains 1 gram equivalent of the electrolyte dissolved in it. Then according to definition, the conductance of solution will be equal to the equivalent conductance. Thus, in this case, conductance G of is equal to specific conductance is equal to equivalent conductance. Suppose the solution is now diluted to 1000 cubic meters. We will be having now 1000 meter cubes of solution. The conductance of the resulting solution therefore will be 1000 times of its specific conductance. But even now, as the solution contains only 1 gram equivalent of the electrolyte between the electrodes, the conductance measured will be equivalent conductance. Thus, in case delta is equal to 1000 into K. If the solution is further diluted to say 5000 cubic meters, there will be 5000 meter cubes of the solution, and hence the equivalent conductance of the resulting solution will be 5000 times its specific conductance. In general, delta is equal to K into rho, K into phi. Measurement of equivalent conductance. Equivalent conductance is given by delta is equal to K into rho. Rho is equal phi is equal to volume of the solution in cubic meters containing 1 gram equivalent of electrolyte. Measurement of conductance. The conductance of a solution can be measured by finding out the resistance by means of a Wheatstone bridge arrangement. The solution whose conductance is to be measured is taken in conductivity cell. The conductivity cell is consists of electrodes which are coated with finely divided platinum. These are welded to PT wires which are sealed through two glass tubes. Here is diagram. You can see the tubes are firmly fixed in an ebonite hard rubber cover so that the distance between the electrodes is not altered during the experiment. The copper wires of the circuit dip in mercury placed in glass tubes to complete the circuit. The cell is connected to a resistance box R on one side and to a long thin wire AB stretched along a scale on other side. Some non-resistance R is taken out of the resistance box. An alternating current of about 1000 to 4000 cycles per second is passed through the solution. The sliding contact D is moved on wire AB so that minimum or no sound is heard in the headphone. Then resistance of the solution by resistance R is equal to length BD by length AD. Thus, by knowing R, AD and BD, the resistance of solution can be calculated. Therefore, conductance of the solution is equal to 1 by resistance of the solution. Determination of cell constant. The cell constant is determined by substituting the value of specific conductance of N by 50 KCl solution at 25 degrees Celsius as accurately determined by Colruyt's, and the value of conductance is observed with the given cell in the relationship. Specific conductance is equal to cell constant into conductance. Cell constant is equal to specific conductance upon observed conductance. Cell constant is equal to 0.002765 upon observed conductance. Measurement of equivalent conductance. Knowing specific conductance as above, the equivalent conductance of the solution can be measured by measuring the specific conductance K with volume phi in cc containing 1 gram equivalent of electrolyte. During measurement of conductance, alternating current is used instead of direct current due to the following reason. During the conductance of DC current, there start electrolysis, which results in change in the concentration of the solution. Product of electrolysis get accumulated at the electrodes and set a back EMF. Variation of specific conductance with dilution. Degree of dissociation of an electrolyte. It is the fraction of the total electrolyte in solution which exists in the form of ions. Effect of dilution. Conductance. The conductance of a solution is due to the presence of ions in solution. Since on dilution of the degree of dissociation of electrolyte is increased and more ions are produced in solution, thus conductance of solution should increase on dilution. Specific conductance. Specific conductance depends upon the number of ions present per cc of the solution. Since on dilution same amount of electrolyte is capable of furnishing a large number of ions, however increase in the number of ions on dilution is much less than increase in the volume of solution. Therefore the number of ions per unit volume actually decreases, hence the specific conductance decreases. Equivalent conductance. The value of equivalent conductance increases on dilution. This increase is due to the fact that equivalent conductance is the product of specific conductance and volume phi of the solution containing 1 gram equivalent of the electrolyte. Since the decreasing value of the specific conductance is more than compensated by the increasing value of volume, the value of delta will increase with dilution. The variation of equivalent conductance with dilution is shown in figure, where the equivalent conductance at different dilution is plotted against concentration. Equivalent conductance at infinite dilution. The maximum value of the equivalent conductance of an electrolyte obtained at high dilutions is known as the equivalent conductance at infinite dilution. It is denoted by delta node. By infinite dilution, we mean that the solution is so dilute that any further dilution does not produce any change in the equivalent conductance of the solution. Molar conductance. Like equivalent conductance, the molar conductance of an electrolyte increases with dilution. Molar conductance at infinite dilution is denoted by delta M node. Cell constant. The specific conductance is the conductance of 1 meter cube of the solution. The conductance measured by using conductivity cell will be the specific conductance only if the electrodes are exactly 1 meter square area and 1 meter apart. This is not usually the case. The conductance obtained will therefore is multiplied by a certain factor in order to get the specific conductance. This factor is called the cell constant, K cell. Since K is equal to L by A into conductance, hence the conductance measured in a cell has to be multiplied by factor L by A in order to get the specific conductance. Evidently, the factor L by A is the cell constant, where L is equal to the distance in M between the electrodes. A is equal to cross-sectional area of the electrodes in meter square. Unit of cell constant is meter inverse. Equation 1 can be written as K is equal to cell constant in conductance. Migration of ions. Electrolytic solution shows conductivity due to the migration of ions. On passing current in electrolytic solution, ions migrate towards positively charged electrode is called migration of ions. The migration of ions through electrolytic solution can be demonstrated by the following method. Take a U tube of uniform cross section, fill the lower limb A band and the greater portion of the limb B with hot 4% solution of gelatin containing few ml of saturated KCl to make it conducting, and few drops of KOH plus a drop of phenolphthalein to make it pink colored. Allow it to cool. When it sets to pink colored jelly, then fill about 3/4 of the remaining portion of a limb with hot solution of gelatin plus KCl plus a drop of phenolphthalein. Allow it to cool. When it sets to form a colorless jelly, then fill the remaining upper portion of limb A and B with KOH and HCl solutions respectively. Finally, dip 2 platinized platinum electrodes in the solution. In this way, the negative electrode is in contact with QH solution while positive electrode in contact with HCl solution. Relative speed of ions. On electrolysis, most of the ions differ largely in their mobilities. L their equal numbers are known to be discharged at the appropriate electrodes. Titov explained this with the help of theoretical device represented in figure. V is the vessel containing the solution of electrolyte giving equal number of positive and negative ions of the same valency. The two metal electrodes A and B represent the anode and cathode respectively. The vessel is supposed to be divided into three compartments by putting imaginary partitions at C and D, which are permeable to ions. The three imaginary chambers AC, CD and DB are termed as anodic, central and cathodic compartments respectively. Before electrolysis, the position of the solution is represented in the figure. There are say 8 pairs of positive and negative ions in anodic and cathodic compartments and 6 pairs in the central compartment. Now suppose that on applying potential only cations are capable of moving and that in a given time two of the cation move towards the cathode. The condition will then be as represented in the figure at 2. There will be two unpaired cation in the cathodic compartment. There will also be two unpaired anions left in the anodic compartment. An unpaired ion always gets discharged at the respective electrodes of electrons as case may be. Two cations will be discharged at the cathode and two anions would be discharged at anode. Thus the same number of cations and anions will be discharged at cathode and anode respectively, even though the cations were able to move. Now suppose that both the cations and anions can move and that both have the same speed. Thus if two cations move towards the cathode and two anions will move towards the anode in the same time, the condition will then be represented in the figure at third. Now 4 cations and 4 anions, the same number will be discharged. Transport number. It is also called transference number or Hittorf number. The fraction of the total current carried by each ion is called its transport number, or the fraction of total current carried by one of the ionic species is known as number of the species. If U plus is the mobility of cation and U negative is mobility of an ion, then transport number of cation T positive is equal to current carried by the cation upon total current is equal to U positive by U positive plus U negative. Transport number of anion T negative is equal to current carried by anion by total current U negative by U positive plus U negative. Further, since T positive plus T negative is equal to 1, it follows that if transport number of one of the ions is known, that of other can be easily calculated. Determination of transport number. Hittorf method, moving boundary method. Determination of transport number, Hittorf method. This method is based on the concentration change observed in the vicinity of the electrodes. Mobility of cation U positive upon mobility of anion U negative is equal to fall of the concentration round anode is equal to upon fall of concentration round cathode. Transport number T positive is equal to U positive by U positive plus U negative. T positive is equal to fall of concentration round anode by fall of concentration round anode plus fall of concentration round cathode is equal to fall of concentration round anode by total fall of concentration. If concentrations are measured in terms of gram equivalent, then T positive is equal to number of gram equivalents lost from the anodic compartments upon total number of gram equivalents lost from the both compartments. Total number of gram equivalents lost from both the compartment is equal to the number of gram equivalent deposited on each electrode. T positive is equal to number of gram equivalent from the anodic compartment by number of gram equivalent deposited on each electrode. Since according to Faraday's second law, the number of gram equivalent deposited on each electron must be equal to the number of gram equivalent of copper deposited in an copper coulometer by say quantity of electricity. For this, a copper coulometer must be connected in series with the experimental solution. T positive is equal to number of gram equivalent lost from the anodic compartment by number of gram equivalent of copper deposited in the coulometer. Also, since T positive plus T negative is equal to 1, T negative is equal to 1 minus T positive. It may be noted that the transport number of an ion does not depend upon the mobility of the ion alone. It also depends upon the mobility of the other ion with which the associated, because by definition T positive is equal to U positive by U positive plus U negative, and T negative is equal to U negative by U positive plus U negative. Determination of transport number. Moving boundary method. The moving boundary method based on direction observation of migration of ions in an electric field. The principle may be expanded with reference of determination of transport number of H positive ions in hydrochloric acid. The conductivity cell in this method consists of a vertical tube of uniform bore filled with cadmium chloride and hydrochloric acid. Hydrochloric acid is the principal electrolyte, while cadmium chloride serves as the indicator electrolyte to enable formation of boundaries. The concentration of solutions also adjusted that HCl solution is lighter than the cadmium solution, therefore floats over cadmium chloride solution. A sharp boundary appears between two solutions. The selection of the indicator electrolyte has to be made carefully. Its cation should not move faster than the cation whose transport number is to be determined, and it should have the same anion as the principal electrolyte. Cadmium chloride fulfills both these requirements. The mobility of cadmium is less that of hydrogen, and it has common anion with hydrochloric acid. The anion at the bottom is of cadmium metal, while the cathode at the top is platinum foil. When a small current is passed through the conductivity cell, the chloride ions move towards the anode, while hydrogen ions are followed by cadmium ions move towards the cathode. The boundary separating the two solutions move upwards as indicated by an arrow in the figure. If the boundary moves through a distance L centimeter, then the volume of the liquid that has moved up is L A centimeter cube, where A is the cross-sectional area of tube in centimeter square. Let the concentration of acid be C gram equivalents per liter, then the number of gram equivalents of H positive ions carried towards the cathode, LAC by 1000. Since each gram equivalent carries 1 Faraday of electricity, the electricity carried by H positive ions is equal to LAC by 1000 Faradays. Suppose the total quantity of electricity that flows in the same time as measured in a coulometer is equal to Q Faradays, then transport number of H positive ion is equal to LAC by 1000 Q. Kohlraub's law. The molar conductance at infinite dilution of some pairs of electrolytes have the same cation or the same anion is given in table. It is evident that the replacement of potassium ions by sodium ion is any of the electrolytes produces the same difference in molar conductance at infinite dilution, irrespective of the nature of the anion. Similarly, the replacement of chloride ion by fluoride ion, or the replacement of nitrite ion by iodate ion, produces the same difference in molar conductance at infinite dilution, irrespective of the nature of the cation. In other words, the difference in the molar conductances at infinite dilution of any two cations appears to be the same, irrespective of their nature of the anions with which they are associated. Similarly, the difference in the molar conductances at infinite dilution of two anions is always about the same, irrespective of the nature of the cation with which they are associated. This led Kohlrausch to state that at infinite dilution, when dilution is complete, each ion makes a definite contribution towards molar conductance of the electrolyte, irrespective of the nature of the other ion with which it associated, and that the molar conductance at infinite dilution of any electrolyte is given by sum of contribution of two ions. This is known as Kohlrausch law. Thus, delta M node is equal to delta positive node plus delta node negative. Calculation of molar ionic conductance by combining Kohlrausch's law and result of transport number measurements it is possible to calculate molar ionic conductances at infinite dilution. Transport number of cation T positive is equal to U positive by U positive plus U negative. Equation 1 can be written as T naught positive is equal to U naught positive by U naught positive plus U naught negative. According since lambda naught is directly proportional to U naught, hence T naught positive is equal to lambda naught positive by lambda naught positive by plus lambda naught negative. And this further solves example determine the molar ionic conductance of CH3COO negative. We can solve by this method. This is the solution. You can see applications of Kohlraub's law. Number 1. Calculation of molar conductance at infinite dilution for weak electrolyte. Molar conductance of strong electrolytes and infinite dilution can be obtained by graphical method. This method is not applicable for weak electrolytes, but Kohlraub's law can be used for the determination of molar conductance of weak electrolytes. Example: the molar conductance of acetic acid at infinite dilution can be obtained from the molar conductance at infinite dilution of hydrochloric acid, sodium acetate and sodium chloride, all of which are strong electrolytes as illustrated below. Delta node MCH3COOH is equal to delta node positive H positive plus delta node negative CH3COO negative. Delta node MHCl is equal to delta node H positive plus delta node negative Cl negative. Delta node MCH3CON is equal to delta positive Na positive plus delta negative CH3CO negative. Delta node NaCl is equal to delta node positive plus Na positive plus delta node negative minus Cl negative. Molar conductance of acetic acid at infinite dilution is equal to molar conductance of hydrochloric acid at infinite dilution plus molar conductance of sodium acetate at infinite dilution minus molar conductance of sodium chloride at infinite dilution. Determination of transport number. The transport numbers of ions are related to their molar conductance as follows. T naught positive negative is equal to lambda naught positive negative by lambda naught m is equal to lambda naught positive negative upon lambda naught positive plus lambda naught negative. Further molar conductances are related to their mobilities as follows. Delta naught positive negative is equal to F U naught positive negative. F is equal to Faraday. Thus, if the molar conductance of ion are of their mobilities at infinite dilution are known, the transport number of the ions at infinite dilution can easily be calculated. Arrhenius theory of electrolyte dissociation. This theory was given by Arrhenius in 1884. Main points: the molecules of an electrolyte is in solution breaks up into two of charged particles called ions. The ions carrying positive charge are called cations, while those carrying negative charge are called anions. The total charge of the cation present in the solution is equal, but opposite to that anions present, so that the solution as whole is electrically neutral. These ions are constantly reuniting to form undissociated molecules, and state of the equilibrium between the ionized and unionized molecules exist. The ions are free to move and under the influence of electricity are directed towards positively charged electrodes. Thus, only those substances which ionize in the solution will be conductor of electricity. The properties of electrolytes in the solution are properties of ion produced. The electrolyte at a given dilution may not be completely ionized, and the fraction of the total molecules ionized is termed as degree of dissociation. Degree of dissociation depends upon the following factor: nature of electrolyte, nature of solvent, presence of other solutes, dilution, temperature. The ions behave like molecules in producing properties like osmotic pressure, depression in freezing point, elevation in boiling point, and lowering of vapor pressure. Limitations of Arrhenius theory. Oswald dilution law, which is based on Arrhenius theory, fails completely when applied to strong electrolytes. As strong electrolytes conduct electricity in molten state, also it means that their ionization must have taken place even in the absence of water. Arrhenius theory simply assumes that the existence of ions in solution. It does not explain how and why ions are formed in solution. Arrhenius theory assumes the interdependent existence of ions in solution, which does not take various account that mobility of ions can be changed by applying electrostatic force. Arrhenius theory could not explain the variation of transport number with concentration. The value of equilibrium constant of strong electrolytes were found to vary with the concentration of electrolytes. The rate of neutralization of HCl and NaOH was found to be interdependent on concentration, but their degree of dissociation as measured by conductivity measurement or study of the colligative properties was found to decrease with the increase in concentration. Thus, the heat of neutralization should also decrease with the increase in concentration. The value of degree of dissociation in case of any valent electrolytes like HCl, KCl, it was found good as measured by electrolytic conductivity measurements. Weak and strong electrolytes. Weak electrolytes. A weak electrolyte is a substance that gives a solution in which only a small portion of the solute molecules are ionized. Such a solution is called weak electrolyte solution. Such solutions have low value of equivalent conductance or low conducting. Strong electrolytes. A strong electrolyte is a substance that gives a solution in which most of all the ions molecules are ionized. With such a solution is called strong electrolyte. Such solutions are good conductors of electricity and have high value of equivalent conductance even at low concentration. Post-Wald dilution law. According to Arrhenius theory of electrolytic dissociation, the molecules of an electrolyte in evaporation undergoes spontaneous dissociation into positive and negative ions, and that there is a dynamic equilibrium between ions and unionized molecules. Ostwald therefore applied the law of chemical equilibrium to such systems. Consider an electrolyte ABC moles of which are dissolved per dm cube of an aqueous solution. Let alpha be the degree of dissociation, I fraction of total concentration of electrolyte which exists in dissociated states. Then this will be the whole process. Then the degree of dissociation alpha at different concentration was determined by conductance measurement using following equation. Alpha is equal to lambda node by lambda m by lambda node m. Lambda m is equal to molar conductance. Lambda node m is equal to molar conductance at infinite dilution. The law was found to hold good in case of weak electrolytes such as acetic acid and ammonium hydroxide. However, the law failed completely when it was applied to strong electrolytes such as NaCl, NaOH or KCl. The German chemist W. Oswald was awarded Chemistry Nobel Prize for his work on catalysis in chemical equilibria and rates of reaction. In case of weak electrolytes, the value of the degree of dissociation is very small. Therefore, 1 minus alpha is almost equal to 1. Equation 1 simplifies to this. From equation 3, it follows the degree of dissociation of weak electrolyte is inversely proportional to the square root of concentration. For equation 2, when alpha is small, alpha is equal to root kV. This is equation 4. Equation 4, it follows that the degree of dissociation of weak electrolyte is directly proportional to the square root of its dilution. Limitation. This law is obeyed by weak electrolytes. Only strong electrolytes such as HCl and NaOH, salts, etc. do not obey this law. The value of degree of dissociation of an electrolyte is determined from colligative properties and from conductance measurements often disagree. This law is based on Arrhenius theory, but the Arrhenius theory itself fails when applied to strong electrolytes. Basically, the failures of Ostwald dilution law are due to the incapability of Arrhenius theory of dissociation for solution of electrolytes.